Hi, I'm Dr. Jeff Groh, and this is Calculus 1. Today, we're going to talk about concavity. We'll begin with a definition. We say that a function f is concave up on an interval I if f prime is increasing. On the interval I. The picture is as follows. It's concave up if, as you move along the curve, the slopes get bigger and bigger. You can put your hand like this, cup it, like you're trying to hold water. If the cup holds water, it's concave up. If it goes the other way, it's concave down. And so we'll add to this definition. It is concave down on the interval I if f prime is decreasing on the interval I. Let's look at a couple examples. Suppose I have the function f of x equals x squared. Everyone knows this is a parabola with vertex at the origin opening up. The derivative is the function 2x. Now, does this function increase as x increases? And how do you determine whether or not a function is increasing? Remember from the last lecture, a function is increasing if its derivative is positive. To determine whether or not the derivative is increasing, we need to calculate the derivative of the derivative. Since the second order derivative is positive, the first order derivative is increasing. That means this function is concave up. Let's compare that to another example. The function x cubed. You all know that as a function that has a symmetry through the origin like this. The derivative is 3x squared. And the second order derivative is 6x. When x is positive, the second order derivative is positive and the slopes, f prime, will be increasing. So it will be concave up for positive values of x. But when x is negative, the second order derivative is negative, that means the first order derivative is decreasing. And you can see that on the graph. The slopes get less and less as you go towards the origin on the left-hand side. So on a portion of the domain, the curve is concave down. And on another portion of the domain, the curve is concave up. We have then the following theorem. If the second order derivative exists on an interval, and if the second order derivative is bigger than 0 everywhere on the interval, then the original function f is concave up on I. If the second order derivative is negative for all x in the interval, then f is concave down. And this theorem follows immediately from our theorem in the last section on increasing and decreasing functions. The function is increasing if its derivative is positive. In this case, if f prime has a derivative that is positive, if the second derivative is positive, then f prime is increasing, and that means f is concave up. Alternatively, if f prime prime is negative, that means f prime is decreasing, and that means f is concave down. For example, let's look at a curve that's related to the normal curve in statistics. E to the minus x squared over 2. The graph of this curve is like a bell shape. The first order derivative is, well, the derivative of e to the stuff is e to the stuff, but you need to multiply by the derivative of the exponent using the chain rule. The derivative of the exponent is minus x. To calculate the second order derivative requires the product rule. Derivative of the first times the second plus the first times the derivative of the second we can factor out an e to the minus x squared over 2. What's left over is a positive x squared and a minus 1. You can see then that this factors as e to the minus x squared over 2, x minus 1, x plus 1. This will be 0 at x equals 1 and minus 1, which we'll put on a number line. And we'll check the signs of the second order derivatives along the interval at each of the resulting 3 subintervals. If we plot, say, negative 2 squared is 4, minus 1 is positive. The exponential function in front is always positive. If we plot 0, we'll get a negative, and if we plot something like 2, we get a positive. Just as for increasing and decreasing intervals, we may include the endpoints in either or both of the intervals. We say that f is concave up on minus infinity to minus 1, and again you can use square brackets here, union 1 to infinity. F is concave down on minus 1 to 1. Your homework program probably requires all of these to be rounded parentheses. It will require all of your little subintervals be open. You can see then that on this last example, there are points on each side of the y-axis where the curve switches from concave up and then to concave down, from concave down back to concave up. These occur at negative 1 and 1. Let's look at another example. Let's look at the function x squared plus 1 over x squared minus 4. calculate the derivative, we require the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Remember how we simplify these? Factor first. Let's put some braces around this and take a 2x out of the numerator. What's left over? We have that factor of 2x. We have x squared minus x squared, which cancels. Negative 4 minus 1 is minus 5. And that's over x squared minus 4 quantity squared. We'll simplify this further to negative 10x divided by x squared minus 4 quantity squared. We have here f prime of x, but in trying to determine the intervals of concavity, concave up, concave down, we need the second order derivative. We apply the quotient rule again. Derivative of the top times the bottom minus the top times the derivative of the bottom. Here, we'll bring the power down, subtract 1 from the exponent, and then multiply by the derivative of the inside. And then divide by the denominator squared. So we end up with an exponent of 4 in the denominator. Remember to factor first. In the numerator, you can definitely factor out an x squared minus 4. But you can also factor out a negative 10. The x squared minus 4 cancels with one factor of x squared minus 4 in the denominator. So we still have a negative 10 out front. What's left over? We have x squared minus 4x squared. That gives us a minus 3x squared. We have a minus 4 and nothing else. Over the denominator, x squared minus 4 cubed. We can multiply through by this negative, and now you can see that the numerator is always positive. The sign of the second derivative will be completely determined by the polynomial in the denominator, and that's determined by x squared minus 4. You can see that the second order derivative will be undefined at x equals 2 and also at negative 2. The only place where the second order derivative can change sign is where the second order derivative is either equal to 0 or undefined, just as with critical points. So we plot negative 2 and 2 on our number line, and then 1 point within each of the resulting 3 intervals will determine the sign on each of those subintervals. So plotting negative 3, negative 3 squared is 9, minus 4 is positive, the whole expression will be positive. At x equals 0, we get a negative, and at x equals 3, positive again. We conclude then that this curve is concave up from minus infinity to minus 2, and from 2 to infinity it is concave down from negative 2 to 2. Essentially, when the graph of a function changes from concave up to concave down or vice versa, The point on the graph is called an inflection point. More precisely, the function f has an inflection point at a f of a. Notice that an inflection point is an actual point on the graph. It has both an x and a y coordinate. First of all, f must be continuous, not just at x equals a, but in a neighborhood of x equals a. Second, you have to have a well-defined tangent line, one and only one tangent line. And of course, you have to actually change concavity as you cross that point. So on one side, the second order derivative will have one sign, on the other side another sign. Technically, the second order derivative doesn't need to exist. We said the function is concave up if f prime is increasing. That doesn't imply that the second derivative exists. So f prime is going up on one side and down on the other. Just as with critical points, the only place where the second derivative can change sign is where the second derivative is either 0 or does not exist, and the proof follows in the same pattern. So if a f of a is an inflection point, then either f double prime at a is 0, or f double prime at a is undefined as a limit or does not exist as a limit. D and E stands for does not exist. In the 1972 presidential election, President Nixon said, "The rate of increase of inflation is going down." The rate of increase of inflation is going down. So inflation could still be going up, but the rate of increase has declined. So the rate of inflation could still be getting worse. It's just getting worse at a slower rate. So he's not arguing that inflation is decreasing, just that it's not increasing as fast as it used to. That says something about the concavity of the curve. So for example, find all inflection points of the function x to the fourth minus, let's say, 4x cubed. In our solution, we begin by calculating the derivative. And then the second derivative. We'll factor the second order derivative. It looks like a 12x can be factored out, leaving x minus 2. The only place where you may have an inflection point is where the second derivative is either 0 or does not exist. In this case, if we set the second derivative equal to 0, the only possible x coordinates of inflection points are going to be x equals 0 and x equals 2. How do we know? We have to draw a number line. We have to know that the second order derivative actually changes sign. So we will plot those possible x coordinates of inflection points first, and then test one point within each of the resulting 3 intervals to determine the concavity there. Plugging in something like -1, we get negative times negative is positive. Plugging in 1, positive times negative is negative. Plugging in 3, positive times positive. We can see then that we actually change concavity at x equals 0, and we also change concavity at x equals 2. There will be 2 inflection points for this curve. The inflection points then are x equals 0, y equals 0, and then x equals 2, 2 to the 4th is 16, 2 cubed is 8, times 4 is 32, 16 minus 32 is negative 16. As another example, find the inflection points of the function f of x equals x to the power of 1/3. This function is continuous everywhere. It looks like the x cubed function just laid on its side. You can tell it's going to be concave up on the left and concave down on the right. Calculating the derivative, we have 1/3 x to the minus 2/3. The second order derivative is minus 2/9, x to the minus 5/3. We have negative 2 over 9, x to the 5/3. You can see that the second order derivative does not exist at x equals 0. So x equals 0 is the location of a possible x coordinate of an inflection point. To know for sure, we have to check that the concavity actually changes. Drawing a number line for f double prime, there's only one point to plot, x equals 0, as you can see from the graph. If x is negative, you take the cube root of a negative and get a negative. The 5th power of a negative is still negative. Negative over negative is positive. It's concave up on the left. If we plug in a positive value, we'll get a negative, and so it's concave down on the right. The point 0, 0 is on the graph, having a well-defined tangent line. Recall that f prime in this case was 1/3 x to the minus 2/3, which is 1 over 3 times the cube root of x squared. At x equals 0, the derivative is undefined, but that doesn't mean that you don't have a well-defined tangent line. You do. It just has a slope that's undefined. The tangent line exists. It is unique, and it goes straight up. You only have one inflection point, and it is at the origin, the place where the concavity changes. Let's look at another example. Let's look at the sine function. The first derivative is, of course, cosine. The second derivative is negative sine x. Where is that equal to 0? It's equal to 0 everywhere that the sine function is 0. And that will be the set of all n pi, such that n is an element of the set of integers. So the possible x-coordinates of inflection points are these points, integers times pi. If you look at the sine curve, you can see this. Negative pi, 0, pi, 2 pi, 3 pi, and so forth. These are places where you change concavity. Between 0 and pi, say at x equals pi over 2, sine of pi over 2 is 1, you get a concavity of negative 1. Negative concavity, it's concave down. At 3 pi over 2, you'll get negative 1 or positive 1. It's concave up, as you can see clearly on the graph. The concavity will actually change at each of these possible inflection points. The inflection points are then n pi, comma, 0, the y-coordinates are all 0, where n is an element of the set of integers. As you might have guessed, when we started talking about the first derivative test for relative extrema, that there might be a second derivative test. And in fact there is. As you can see, if you have a critical point of the sort where the slope is 0 at a place where the curve is concave down, that must be a local max. If you have a critical point of the sort where the slope is 0 at a place where the curve is concave up, that must be a local min. We have the second derivative test. For relative extrema. It goes like this. Suppose that f double prime at A is 0, so it's the sort of critical point where the slope is 0. And we must have the second order derivative existing on some neighborhood. If the second order derivative at A is positive, so that it's concave up, then f has a local min at x equals A. A relative min. 2. If the second order derivative at A is negative, so that it's concave down at that place where you have a slope equal to 0, then f has a local max at x equals A. The proof uses the first derivative test, believe it or not. The idea being that if f double prime at A is negative, then f double prime being continuous will be negative in some neighborhood. Containing A. So if the slope there is 0 at this critical point, we'll suppose, of course, f prime at A equal to 0. Now, since the second order derivative is negative in some neighborhood of x equals A, that implies that f prime is decreasing. On the interval I. And since f prime is decreasing, that means, and since f prime is decreasing and f prime at A is 0, that means f prime is going to be positive to the left of A and negative f prime will be negative for x values to the right of A. So it's going up before it gets there and down afterwards. It's here that we apply the first derivative test for relative extrema. By the first derivative test, f has a local max at x equals A. The other case follows similarly. And that's the end of the proof. So, for example, let's suppose our function is x e to the negative x squared. Let's classify the critical points of this function using the second derivative test. So first of all, we need to find what those critical points are. Step 1, find the critical points. We'll calculate the derivative using the product rule. Derivative of the first times the second plus the first times the derivative of the second using the chain rule. Factoring e to the negative x squared out, what's left over is 1 minus 2x squared. If we set that equal to 0, we get x is plus or minus root 2 over 2. 2 critical points. We're going to classify these using the second derivative test, not the first derivative test. So calculating the second derivative also requires the product rule, derivative of the first times the second plus the first times the derivative of the second. Simplifying the second derivative, it looks like we can factor out a negative 2x e to the negative x squared. What's left over is 1 minus 2x squared plus 1, plus 2. And so we have negative 2x e to the minus x squared times 3 minus 2x squared. Remember, x squared will be 1/2 for these two critical points. Evaluating at positive root 2 over 2, we'll have a positive here in both of these cases, but plugging in a positive in the first factor gives us a negative. It's concave down at root 2 over 2. Since it's concave down at a place where the slope is 0, that implies we have a local max. When we evaluate at the other critical point, negative times negative is positive. It's concave up at a place where the slope is 0. It's a local min. Let's classify the relative extrema. Root 3 over 2x minus sine x. First, we find the critical points. Root 3 over 2 minus cosine x. If we set this equal to 0, we're looking for points where cosine x is the square root of 3 over 2. Where are these places? Well, for the sake of this problem, let's constrain ourselves to the interval 0 to 2 pi, say the open interval from 0 to 2 pi. Cosine is positive in quadrants 1 and 4. The reference angle is pi over 6. That gives us the angle in quadrant 1. In quadrant 4, that will be 11 pi over 6 on this interval. To classify these critical points, we need to calculate the second derivative. The second derivative is going to be positive sine of x. Evaluating at pi over 6, we get the sine of pi over 6, which is 1/2, and that's positive, which means we're concave up at this point. We have a relative min. At a place where your slope is 0 and you're concave up, it must be a local min. At 11 pi over 6, we get negative 1/2, which is negative. It's concave down at a place where the slope is 0. That must be a relative max. For our next example, we'll look at x to the 4th plus 1 over x squared. First, we calculate the derivative so that we can find the critical points. The derivative of the top is 4x cubed times the bottom minus the top, x to the 4th plus 1, times the derivative of the bottom divided by the bottom squared. We begin the simplification process by factoring the numerator as much as possible. We can take a 2x out. That'll leave a 2 here. Take one of those x's, a 2 and an x. We'll have the 2x times 2x to the 4th minus x to the 4th is x to the 4th minus 1 over x to the 4th. One of these x's cancels, and we have 2 times the quantity x to the 4th minus 1 over x cubed. Now, the critical points. Critical points are points in the domain where either the derivative is equal to 0 or the derivative does not exist. you can see that plus or minus 1 are critical points. 0 is not a critical point because 0 is not in the domain. If we're to classify these critical points using the second derivative test, we need to calculate the second derivative. F prime is over here on the lower right. Second derivative, this 2 can be left out of this process. Derivative of the top, that's 4x cubed, times the bottom, x cubed, minus the top, x to the fourth minus 1, times the derivative of the bottom, 3x squared, all over the bottom squared. We can factor out an x squared from the numerator. Canceling, we'll have 2 times the quantity. 4x to the fourth minus 3x to the fourth is 1x to the fourth minus a negative 3, so that's plus 3 over x to the fourth. You can see that wherever this is defined, it's going to be positive, which means these both must be local minima. The original function, x to the fourth plus 1 over x squared, looks like x squared plus 1 over x squared. As x gets big, the curve gets closer and closer to the parabola y equals x squared. So if we draw in that parabola like this, also note that as x gets closer and closer to 0 on each side, this function blows up and goes to positive infinity. So the curve will do something like this, always a little bit above the curve y equals x squared, and asymptotic to going to infinity at the origin. The location of these two minima are at minus 1 and 1, as we have seen. Stating our answer, f has a local min at both x equals minus 1 and x equals 1. You might remember from basic physics that if you launch an object at some angle theta without air resistance, neglecting air resistance, the path of the particle, if we're assuming x naught is equal to 0, is going to be the initial velocity. We'll have some initial speed v naught times the cosine of theta times t, and we'll have y naught plus v naught sine theta times t minus 1/2 g t squared. If we solve for t and substitute, we get y equals y naught plus, if t is equal to x divided by v naught cosine theta, the v naughts will cancel. We'll have tangent theta times x minus 1/2 g t squared. That's going to be x squared divided by v naught squared cosine squared theta. We'll set y naught equal to 0. The range is the x value when y equals 0. We'll assume that x is not 0, so the range is not 0 in this case. So both y naught will be 0 and y is 0. You can see that we can factor an x out. And we can then solve for the range. Assuming that x is not 0, we can divide this factor of x off and then solve for x. We're setting this expression equal to 0 and solving for x. We'll move this term to the other side and have g over 2 v naught squared cosine squared theta times x equals tangent theta. The range x then is going to be tangent theta times 2 v naught squared over g times cosine squared theta. Tangent is sine theta over cosine theta. We can cancel one factor of cosine theta. Keep in mind that the sine of 2 theta is 2 sine theta cosine theta, which we happen to have, 2 sine theta cosine theta. So we're going to have v naught squared over g times the sine of 2 theta. The next question we want to ask is, what value of theta maximizes this range? We'll assume that theta takes values between 0 and pi over 2, no more than pi over 2. Of course, at pi over 2, the range will be 0, because the projectile will go straight up and then straight down. So we can eliminate both 0 and pi over 2 from consideration. To find the maximum, which you probably know already to be theta is 45 degrees, we need to calculate the critical point. The critical point occurs at dx d theta equal 0. That's going to be v naught squared over g times 2 times the cosine of 2 theta. All of these constants can be canceled off, and we're just looking for where cosine is 0. Well, cosine is 0 at pi over 2, so we deduce that 2 theta is 90 degrees, or theta is 45 degrees. That shows us that theta equals 45 degrees is a critical point, but is it a local max? And there is something called the unique critical point theorem. If you have a unique critical point on some domain, then that's either a max or a min. To classify this critical point, we need to evaluate the second order derivative at the critical point. The second order derivative will be minus 4 v naught squared over g times the sine of 2 theta. If theta is 45 degrees, 2 times 45 is 90. The sine of 90 degrees is 1. And so we get a negative, if we evaluate it, theta equals 45 degrees. We get a negative second order derivative. It's concave down at a place where the slope is 0. That implies a max. We get a maximum range when theta is 45 degrees and when there's no air resistance. If there is air resistance, projectiles don't follow nice parabola. They fall a little short. So it actually pays to go a little bit higher than 45 degrees to reach that maximum range.